Let us talk about cables. There are different types of systems that have cables. There are cables with concentrated loads and cables with distributed loads. The first case is when we have a cable with a concentrated load. Um, in that case, for instance, is when we have a thin cable or rope that is holding different things from ornaments or from um, points at the ground that the cable is um, holding things together, whatever this is. There are different tensions, different forces, and in this case, we would have a fixed point at A and B. Before, with beams, you remember that there are points that you don't need fixed. Like at B, you can only have a force in A with a roller because the beam itself was rigid. But here, in for the case of the cable, we have we have to have two fixed points at least. You can have more fixed points. If it's a three-dimensional problem, you're probably gonna have a lot of fixed points. Here you have A and B, and the rest are going to be weights. For this to be static, meaning that it's not moving, first you have to hang the loads or have tension on the cable or the wire, wait for it to stabilize or tension the wire to a point that is stable, and at that point you're gonna have different aspects. First, notice that we have these lines right here, shaded strokes, where it's letting us know that depending on the configuration of P1, P2, and P3, you're gonna have that um, behavior of the cable. So if they're like cars, this is a bridge and there are cars going through. I'm exaggerating this a little bit, but you have this movement depending on the loads, and this is allowed. This is okay. That's the design. You want things to have some flexibility and to have some movement. You don't want too much, but you don't want to have completely rigid because then you can crack. So that's why cables are so beneficial because you still have some dynamics, some displacements, but still the structure itself is going to be um, sound and static. The other thing is that each point will have its own tension. So evidently you're going to have a tension right here and a tension right here, a tension right here, and from A to C1. Also, you're gonna have angles. So you're gonna have alpha. This one is pretty small, but you can see it there. You're gonna have beta. You're gonna have theta, etc. So all these angles need to be determined. Gamma. It's important to determine because if you change the angle, as you've seen before with the vector, you have a magnitude in that direction. If they change too much, then the tension could become too high. So it's important to know this configuration, and usually the engineer will put this down for the architect or whoever is building the system to know um, what is the angle of this tension with respect to the fixed point. Obviously, you have to know the distances from each load to the point, and then you can do the thing that you've known all this time. Summation of forces in x equals 0. Take a positive direction, usually to the right hand side. And here you're going to have forces on x, and before we didn't have forces in x very often. Here you're going to have forces on x when, at the fixed points. So ax and bx. So for this configuration, ax is equal to bx. All right, and then summation of forces in y, you're going to say positive going up. You're going to have ay plus by. We don't know those, but we do know the forces. P1, P2, P3. Okay, so we have AX and BX, we don't know those. We have AY and BY, we don't know those. So we have two equations for our unknowns. ax, bx, ay, by. So from those equations, we cannot solve what we need. So we can start doing moments. And this is the nice thing about cables, that if you have the distances, it's very easy. You could do moments at points or cut somewhere where you care about your moment. So if you have the distance to D, you can easily do that distance there, your moment there. Since we have the distance to C, we can have distances with respect to those points. So if you do summation of moments, say at C2 or at D, let's do summation of moment at D. We can do both. We need to do both. Summation at point D, counterclockwise is positive. This is equal to 0. So we have this distance y and this distance x. In case they're asking for distance y, this is how you do it. If you care about this point right here, you would set it up as this is rotating clockwise, so this is a negative moment. This is rotating clockwise, so this is a negative moment. This is rotating counterclockwise, so this is a positive moment. And t is passing through the point, so this is 0. What we have is, let's say, the positive one first. So P1 times the distance from P1 to D, which is x minus x1, then the negative moments, minus ax times the distance that we care about, which is y, minus ay times x. So in this configuration, we know everything except for y. So we can solve for this. Well, I jumped the gun. We don't know this yet. Well, we can find it. We do know P1. We know P1, we know x, we know x1. They're asking for y, we know x, but we don't know ax and ay. So that's why we would want to do summation of other points. So that distance should be known because it's the point where the load was located. That's for design purposes. So this distance should be known. So when you do summation of moments at C2, it's going to be equal to 0, and then choose the direction. Counterclockwise is positive. So we know that, again, we have ay is clockwise, so negative ay times x2, ax is clockwise, so it's negative ax times y2, and P1 is counterclockwise, plus P1 times x2 minus x1. This is equal to 0. From here, we know x2, x1, and y2. Again, if you don't know any of those, then you set up the equation and keep building your system of equations. So from here, if we know, let's say we do know y2, then we have one equation where the unknowns are ay and ax. And if you remember, there's an equation right here where the unknowns are ay and by. So we need to set up an equation where we can solve for one of those. So we're still not able to, well, ay, by, and this is, okay. So in this case, for instance, when we find y, we can do ax and bx. So if I noticed this equation has ay and ax, and this equation has ay and ax. So these two equations can be used for finding ay and ax. So two equations, two unknowns. But with what I would do, remember, you always want to find the ay and ax that are the maximum. So what we did here was we cut at D and then we cut at C. So that's probably not going to be very useful because they're at the points next to each other. But what we can do is do summation of point B. If we want to find AY and BY and AX and BX, let's do summation of moments at point B equals 0. And then in that case, we can do AX is positive, so counterclockwise is positive. So let's do P1 times L minus X1 plus, I'm going to do the positive moments first, P2 times L minus X2 plus P3 L minus X3. All of these information is known. The loads, the distance L, the distance X1, X2, and X3. What is not known are AX and AY. So for that, we have the negative contribution of AX, which is AX times D minus AY times L. This is equal to 0. So this is good news because at this point we have AX and AY in a single equation. And here, from moments at C2, we have AX and AY at a single equation. So you start building your system of equation and then you start solving for AX and AY. The most important ones to have first are the whole system. So this one is a must. This one is a must because it's a moment at B where you have AX and AB, where you have the contributions of all the forces. Okay, so after you solve for AX and AY, which we have AX and AY right here, and we also have AX and AY right here, then what we can do is go and find BY. All right, and then when we find BY, we have BX as well because AX is the same as BY with opposite signs. And then we can start finding the tensions in each cable. Obviously, to find the angle, so for instance, alpha would be this distance and that distance. Let's say this distance is x4 from this point to this point. Say that's x4. And this distance is d4 from that point to this point. So, as you know, the angle alpha will be tangent inverse of d4 divided by x4. And then this tension right here at point C3 is equal to the tension times cosine, well, that will be dx. The contribution at x will be tc3 times cosine of alpha. And the contribution at y, c3y, is equal to dc3, this tension that we care about, times sine of alpha. Right? So if you do not have the tension, what you do have is the angle MP3. And then you can form that triangle right there, where this is alpha and this is your P3. And then you care about your tension, C3. Okay, so in that case, you can use sine of alpha. We'll see an example in a few minutes, and then we'll understand much better how to solve for each force and each angle. All right, now the second case is when you have a cable with distributed loads. So in that case, in this case, the cable itself could be heavy, kind of like when you see in a bridge. The cable itself is made of iron stripes or something that is tough enough to resist tons of weight. So the cable is pretty heavy. And of course, as you can see, you have the restrictions at A and B. So this is by and this is bx, and the same thing at ax and ay. All right, ax and ay. So the cable itself is heavy, so has a distributed load. Sometimes it's not very easy to characterize the load. So what we do is we approximate by, as we did before, a single load at a point. So the load W from, say, point C and point D, and another one from point A and point C, etc. You just start cutting your cable, and then what you have is this tension right here. And if you notice, if this is your x-axis and your y-axis, this force is with respect to the x-axis. That's why we cut it at point C. And that's why we specify point C to be right at the minimum. So your force vector would be your force W, which is the distributed load to a point. This is just the area under this distributed load. You have to integrate, or you can just characterize as a parabola and approximate. Then you have the force T0 or TCX, whatever you like naming your forces better, and the actual T tension from the wire, from the cable. This is in X and this is W. So with those three forces, you can definitely find your magnitude. So the tension in the cable is equal to the square root of your Tx squared plus the distributed load squared, which is right here. Again, you can do the angle, which is tangent inverse of W over Tx. And to find the force itself, you can use cosine or sine that from the angle. So get used to using your tangent, because it's going to be usually the way to find the angle. And then the tension is from your cosine and sine. And remember, tangent of the angle is the y contribution divided by x, y over x. So this is y divided by tx. So the complicated part here, the most difficult part really, is to find W. So hopefully they give you W. If not, you have to find it either by integration or by doing some area under the curve of a known shape, like a parabola or a bunch of parallelograms. You can sometimes you can approximate it as this, and then as that, and then as another parallelogram, depending on how you're able to set this up. And then you have W here and a W here, and then a W here, etc. So in that case, you have a very specific case, which is the parabolic cable. The parabolic cable is the case where we just saw, specific case where C is the minimum. You specify C as the minimum, so that C is the point, the lower point, where you can have information of your X, Y, and your angle. So as we said before, the weight of the cable or the distributed load could be either or. Could be the cable plus a load, or it could be a load that is distributed across the cable, like in a bridge. You find that distributed load as we have before. That is going to be W. Is usually W times X, but really what it means is the area under this curve. And if you cut at C, you have this area and that area. Area to the right and area to the left. So when you place your W, you place it in a way, you follow the table that we've seen before. If it's a parabola, it could be at x over 2. If not, if it's a triangular shape or whatever, if this is completely in tension, then it's probably going to be a triangular shape, a triangle, where you find the W and place it at 1/3 or 2/3 of the base, depending on where you are. Okay, so in this case, it's the same. The only change that we have is how you compute W, which is the most difficult part. So your tension is the same. You form your triangle, you have a tension, you have weight, and you have your point X. So the key is to find your point X to be at the minimum, so that could be a complete horizontal force. That's the contribution of X at that point C. And then here's the same thing. W is really small w times X. So the tension is square root of the contribution in X squared times W squared. So that's W squared times X squared. You find the angle as we mentioned before with tangent inverse of W divided by the X contribution, so Wx, which is Y, and this is X. And then if you need to find a distance, then that's where you do your moments, because the moment is force times distance. So that distance is where you can find with a moment you can find distances. So if you say again moment at D, this is cancelled. So you have T, positive T times Y, so T is X, I mean. So let's do summation of moments at D equals 0. We're trying to replicate this. We're going to have this force in a clockwise moment, so it's going to be negative Tx, declare TO, T0, or T naught, Tx times x half plus x half is x. But really, what our distance is in y, so y, Tx times y. So this is negative Tx times y. And then we have W, which is a positive moment, because it's going counterclockwise. So W times, now this is a horizontal distance, W times x over 2 is equal to 0. But if you notice, we need to replace the capital W for the little w. The force is really the whole area under the curve, you know, so this should be pretty straightforward. So W times x squared, W is small w times x squared is equal to the other side, Tx times y. This is really W x squared over 2 is equal to T x times y. So if they want to find y, which they have it here, trying to get back to the same point, is W x squared over 2 Tx. Yeah. So as you can see, this is a formula given for you. We just did the same thing here to show you how we got there. You just need to read this moment at D. So if they ask for D, if you want to create the whole formula, the whole expression, you should and you can. But if you just put this on your notes, every time that you have a distributed load, parabolic, it has to be parabolic load, and they ask you for a point Y with respect to, well, you know, this point Y really here, the only thing you have to know is X and Y. If this point here was, if they call this point here what they need, say this is D or E or whatever, so then you cut here, and then your distance would be this X and this Y, and that moment would be there, and then you simply apply this formula to know this distance Y. From that distance Y, you can find your angle and then do the whole thing once again. So let's do an example.